Assalamualaikum and good day. My name is Nurul Asmira binti Zalani with matric number KA18044. Would like to present the research and development in the membrane separation process of the forward osmosis. So the development of the membrane technology is one of the most important technology for the water treatment field. So the conventional pressure driver membrane process use high hydraulic pressure, which accelerate the energy consumption and produce a low water recovery. So meanwhile, the forward osmosis is an effective technology that does not need high hydraulic pressure as compared to the reverse osmosis process. So this will lead to the minimum energy consumption and also low irreversible fouling perspective. So besides, the forward osmosis also can be used to separate the different contaminants, achieving a great water recovery rate. So, what is the forward osmosis? So, the forward osmosis is basically a water separation process which uses a semi-permeable membrane and also the natural energy of osmotic pressure to separate the water from the dissolved solutes. So, this osmotic pressure is used to transport the water through the membrane while retaining all the dissolved solute on the other side. So, how does it work? So, the forward osmosis (FO) utilize the osmotic pressure difference developed across the semi-permeable membrane, separating the two solutions of the different concentration to drive the permeations of the water. So, when the two solutions of the different concentration are placed on the two sides of the semi-permeable osmotic pressure differential will generated to drive the permeations of the water across the membrane from the low concentration solution to the concentrated solutions. So during the FO process, the draw solution faces the membrane support layer, while the feed solution faces the active layer of the membrane. So the draw solutions are located reversely, comparing it to the pressure retarded osmosis. So the osmotic pressure difference drive the water transport, and the chemical potential gradient determines the solid transport. Okay, next is the literature view. So, the main objective for the forward osmotic wastewater treatment is the new membrane technology, the draw solutions to improve the wastewater treatment and also the energy recovery and the operating condition of all focusing on the forward osmosis wastewater feasibility. Besides, the prompted by the increasing growth and expansion of the water reuse industry, strive the outline of the remaining step of the FO to achieve the full scales of the wastewater treatment. So therefore, the FO work as an alternative membrane method that has potential to cleanse the wastewater and also produce a high quality water. Besides, the FO also for the treatment of the complicated feeds is being pursued due to its potential advantages over the present technology. Meanwhile, the FO may be built and altered to treat a wide range of the feed types, including the textile industry waste, landfill leachate, and municipal wastewater effluents. Okay, so from this slide, as we can observe from the left side, we continue with the desired characteristic of the FO membrane for the use in wastewater applications. A dense and ultra thin FO membrane is desired since it will have an active separating layer for the high solid rejections. Besides, a high affinity for the water hydrophilicity also desired to enhance the flux and also reduce the fouling propensity. Then an open hydrophilic SL with the high mechanical stability and reducing ICP will contribute to the sustain at the long-term operations. So on the right side, on the other hand, we got the technique used in developing the FO membranes. So the tailoring the membrane surface technique is decrease fouling and improve the water fluxes by functionalizing the membrane surfaces. Besides, additional of the error response nanofibers will increase the mechanical strength. Meanwhile, the re-engineering the support structure to withstand the stress and employing the advanced extrusions technique for the mechanical stability and also the high power density. Okay, so for the membrane orientations, impact to the FO performance significantly. So the tabulated table explains the two modes available for the membrane orientations. The FO modes hinders a good mixing of the draw solutions, then they permeate in the membrane supports and decreasing the mass transfer rate subsequently resulted to the less draw solid reaches the selective layer, which causes a decrease in the driving force. This is referred to as a dilutive ICP because it occurs in the support. On the feed side, the water flow pushes the solid from the feed solutions toward the surface selective layer, which resulted to the concentrative ECP. So meanwhile, the PRO mode also suffer a dilative ECP and also concentrative ICP. Therefore, the fabrication of the optimal FO membrane this on resolving the ICP issues, which mostly caused by the salt build-up in the non-ideal in the non-ideal fit. Meanwhile, the PRO mode considered is the impracticable in many applications due to its high cooling environment. Next, next is the draw solutions. So the performance of the process will not only depends on the material, but it will greatly depends on the selections of the suitable DS as the main sources of the driving force. So the DS will be best appropriate for a certain application. So as we can observe on the figure on the right side, the NaCl appears to be the most employed DS due to its high solubility, but it also low cost and relatively high osmotic potentials. Besides, the DS with the nanoparticle as shown in the left side, in particularly hydrophilic magnetic nanoparticle, also have become an area of the greatest interest. Their main advantages is their extremely high surface area to volume ratio and their bigger size compared to the salts and organic molecules. Next we tabulated the table shows the example of the draw solutions and the draw solutions types available. So in addition, as we can observe, each draw solution contains different advantages and disadvantages itself. Next, few consideration must be taken in selecting the membrane module configurations, such as the economic consideration, fueling propensity, and also the ease of fabrications into the module's design and suitability. So some example of the membrane module configuration is spiral one, hollow fiber, and also the plate and frame. So consideration of the membrane module is very important since as the configuration contains the advantages and disadvantages. Therefore, consider a membrane module configuration before selecting is very crucial in order to ensure we can gain the fullest benefit of it. Okay, next is the development of the high performance clean composite forward osmosis membrane. Okay, so from this slide, it shows the development of the high performance thin composite FO membrane. So commonly, the commercial membrane made up of the cellulose triacetate CDA easily degrades when it is exposed to the ammonium bicarbonate, draw solutions, and have a limited pure water permeability and also salt rejection. Then we develop into the conventional thin film composite as an alternative, have a high salt rejection and meet the chemical stability requirement. However, it performed a poorly FO since it designed for the pressure driven membrane process such as RO. Thus, with development towards the thin composite forward osmosis membrane resulted to the improvement of the performance by the ideal supports layer for the FO membranes would be very thin and porous. Okay, next observations of the membrane's performance. So, it shows the comparison of the forward osmosis water flux and also salt rejection between TFCFO and also membrane and also the other commercial membrane. So as from the observation, it is expected that the thin film composite membrane generally have a higher rejection rates than the asymmetric membranes. The TFCRO membrane have the average salt rejection 98.9%. Meanwhile, the TFCFO membrane develop have the average salt rejection 97.4%, which is slightly lower compared to the TFCRO. Okay, next is the advantages and disadvantages in way forward. Okay, so the advantages and disadvantages of the forward osmosis. So the advantages is treating the more than 70,000 ppm, low energy, reversible fouling, and also low chemicals. The disadvantages is the internal concentration polarization, reverse salt flux, choosing the right draw solutions, and also choosing the right membranes. Okay, so the advantages of the forward osmosis is it operates it it operate at the low and or no hydraulic pressure. The FO require up to 90% less energy compared to RO process to drive the water transport. It may also have a lower membrane fouling prosperity than the pressure driven process and also some of the other advantages. Next, this is the drawback of the forward osmosis, which is the recovery step in closed loop and water recovery system, incomplete rejection of trace organic contaminants, low water flux, and also reverse salt diffusions. Okay, so the current research. Okay, extensive research has been carried out worldwide to explore the potential of FO in desalination, water and wastewater treatment, also the reclamation. So we carry out the database to identify the global research trend and also to resolve the FO challenges such as the high reverse solute flux, concentration polarization, weak membrane mechanical strength, and also intensive energy consumption to ensure the FO can be truly competitive compared to the other technology. So there are five main aspects in order to expected to directed in order to grow and also the mature research of the FO osmosis. FO, which is the forward osmosis. So first is replication of the new FO membrane for the improved performance. Second is the development of the novel FO process to be used in various applications. The third one is the analysis of the fouling phenomenon and associated approach to counter the fouling issues. And the fourth one is the modeling, including the mathematical modeling and also stimulation modeling. And the fifth one is the exploration of different type of draw solutions. Okay, as to summarize, the rising interest of the FO from the numerous disciplines derived from the fact that FO can be used in a wide range scientific and engineering domains, including the water and wastewater treatment, desalination, also the food processing. So the FO have been proposed as a potential candidate for the wastewater treatment due to its high rejection capacity and also low fouling propensity. So another crucial step forward furthering the FO process is the development of the draw solution that can create a high osmotic pressure, since a greater grasp of this idea will encourage the implementation of this technology in both present and also the new wastewater treatment applications. So as a result, the forward osmosis technology can be considered gaining a popularity since it is viable, cost effective, and also dependable options. Thank you.